This video is all about rate of change. Now, before calculus, the best we could do was calculate the average rate of change. But now that we know calculus, I'll be able to show you how to find the instantaneous rate of change. Informally, we think of rate of change as indicating how fast something is happening. Let's take a look at this graph. Imagine that this represents a car that has traveled a certain distance in a certain amount of time. So at this position right here, the car has traveled 250 miles in 10 hours. Now, if we reduce this, that comes out to be 25 miles per hour. So in this case, we've got the rate of change, 25 miles per hour. That's going to be the speed of the car. Now, let's compare this to the slope of the graph. In general, we know that slope is the change in y divided by the change in x. So for this car, the change in y is right here. That's your 250 miles. And the change in x is the time right here. That is your 10 hours. So obviously this is the exact same thing that we got before. So the takeaway here is that rate of change is just the slope. The slope is the rate of change. Look at another example. Imagine a car that went the same 250 miles in 5 hours. That graph would look like this. All right, and let's compare. So this car went 250 miles in 5 hours. If you do that division, it comes out to be 50 miles per hour. So we have a faster rate of change, 50 miles per hour compared with 25 miles per hour. Now look at the slope. Notice this graph has a steeper slope. So again, rate of change is just the slope of the graph. The steeper the slope, the faster the rate of change. Graphs like this are very unrealistic. Cars don't behave like this. This green graph shows a car moving at a constant speed of 50 miles per hour right from the beginning. When you step on the gas, a car doesn't immediately go 50 miles per hour. In the real world, a car will have gradual changes in speed. And during the course of a journey, it'll be going slower sometimes and faster other times. Notice that this graph is showing different slopes during different parts of the journey. That indicates that the speed is changing as we move throughout this graph. When you have a nonlinear graph like this, our pre-calculus skills will let us down. It's impossible to, for instance, figure out the speed of the car at this particular point. The best we can do is find the average rate of change between 2 points. So let's say if I want to find the average rate of change on the time interval from 5 to 10, then I'm really just finding the slope of the segment that goes from 5 to 10. So the rate of change is still just going to be the slope. And we know that the slope is the change in y divided by the change in x. In other words, it's y2 minus y1 over x2 minus x1. So if you're finding the rate of change, you're just really finding the slope. I'm going to put ROC for rate of change. So the change in y is just going to be 250 minus 50. And the change in x is going to be 10 minus 5. So that's going to be 200 divided by 5. So that's going to be 40 for an average rate of change of 40 miles per hour. Let's take a moment to talk about the difference between velocity and speed. The bottom line is that velocity has direction. And speed doesn't. So normally the way we will show direction when we're talking about velocity is with a plus sign or a minus sign. So for example, if I say that a ball is traveling at 25 meters per second, if I put a negative sign on that, negative 25 meters per second, that negative sign indicates that this is either going down or to the left. A positive 25 meters per second would indicate that the ball is traveling either up or to the right. Speed has no direction. So in both of these cases, you would just say 25 miles per hour. All right, the speed is just flat 25 miles per hour. It doesn't include any plus or minus for direction. And for that reason, we can say that the absolute value of velocity equals the speed. The speed is always positive. Example 2, a rock is dropped from a height of 100 feet. The rock's height s at time t is given by the position function s equals negative 16 t squared plus 100, where s is measured in feet and t is measured in seconds. Find the average velocity over the time interval 1, 1.5. So as soon as they say find the average velocity, that's average rate of change. We are looking for the slope. But to get us started, I find it helpful to make a little chart. Okay, so instead of x and y, I'm going to have t and s. So understand that when they give us this time interval, they are giving us x values. Well, okay, not x values, they are giving us t values. All right, it's a time interval. These are t values. All right, both of them. So we have a t value of 1 and we have a t value of 1.5. So we need to find the position values that go with these time values. In other words, for starters, we need to know what the position at time 1 is. S at 1. So that means substituting 1 in for t. So that'll be negative 16 times 1 squared plus 100. That turns out to be 84. Okay, now what about the position at 1.5 seconds? So we're talking about negative 16 times 1.5 squared plus 100. Pop that in your calculator and you get 64. So we are being asked to find the average velocity. But the average velocity is just the average rate of change, which is just the slope, which normally we say y2 minus y1 over x2 minus x1. But in this case, instead of y's, we have s's. Instead of x's, we have t's. But same concept. So as we go to set up the slope, our y2 minus y1 is 64 minus 84 over 1.5 minus 1. So this is going to be negative 20 divided by 0.5, which turns out to be negative 40. So let's put those units in there. We are talking about feet per second. So this is negative 40 feet per second. Notice that the negative sign in front indicates that the rock is falling down. So far, this has all been pre-calculus stuff. Finding the average rate of change over an interval, we're just finding the slope, y minus y over x minus x. It's time to up our game. What if we wanted to find the rate of change right at a specific moment in time? So now we're talking about the instantaneous rate of change, and we're still going to be using the slope, but now we're going to be using the slope of a tangent line at that particular point. In other words, instantaneous rate of change is the slope of the curve at a point. Where have I heard that before? That's right, it's the derivative. In other words, if the position function is s at t, then the velocity function will be s prime at t. Example 3. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. Because the initial velocity of the diver is 16 feet per second, the position of the diver is s at t equals negative 16t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. So, 2 questions. First of all, when does the diver hit the water? And second, what was the diver's velocity at the time of impact? Let's start with when does the diver hit the water? So we've been given the position function. This tells us how high the diver is above the water. So when the position is 0, that's when the diver hits the water. So all we have to do is substitute 0 for position and solve. So that means we're going to have negative 16t squared plus 16t plus 32 equals 0. So if we solve for t, that should be the time of position 0, the time the diver hits the water. So the easiest way to solve this would be to factor. First of all, notice that all of these are divisible by 16. So let's start by pulling out a common factor of negative 16. So if I divide everything by negative 16, I'm going to be left with t squared minus t minus 2. Now let's go ahead and factor the trinomial. So I'm going to keep the negative 16 for now. This trinomial should be easy to factor. T squared is going to be t times t. 2 is 2 times 1. I see that the middle is a negative 1, so I'm going to go for a negative 2 and a positive 1. So there we factored it. The solutions will come from the zero product property. If I set t minus 2 equal to 0, that's going to give me a solution, and t plus 1 equals 0, that'll give me a solution. So adding 2 to both sides, I get t is equal to 2. Subtracting 1 from both sides, I get t is equal to negative 1. Negative seconds, that's not a thing. So this solution is extraneous. So the only one that makes sense in this context is 2 seconds. So that's how long it takes the diver to hit the water, 2 seconds. Now it's time to find the diver's velocity at the time of impact. Keep in the back of your mind that we know that the time of impact is 2 seconds. That's what we just found. The key is that we can turn this position function into a velocity function by taking the derivative. So if we do the derivative of this position function, we will have velocity. Remember that when you have a sum or difference, you're allowed to take the derivative of each term separately. So first I'm just going to take the derivative of this term. And when you have a constant in the front, you can just keep that constant and then do the power rule on the t squared part. So I'm going to put the 2 in the front and then reduce the power by 1, but that'll leave a power of 1, which I don't even need to write down. Then I will move on to the second term. But when you have the derivative of a constant times a variable, it's just going to be the constant. So I'm just going to have plus 16 now. And finally, when I do the derivative of the third term, I remember that the derivative of a constant is 0. So I will put nothing for that. All right, so my velocity function is going to be negative 32t plus 16. So now that I have a velocity function, this will tell me the velocity at any time t. So all I have to do is substitute t equals 2, and that will tell me the velocity at 2 seconds, which is the time of impact. All right, so the velocity at 2 seconds would be negative 32 times 2 plus 16. So that turns out to be negative 48 feet per second. So that is the velocity at the time of impact. Notice that the negative sign indicates that the diver was falling.